In the world of mathematics, a function acts like a machine. Just as a machine takes raw materials and processes them into finished products, a function takes an input and transforms it into a specific output. It takes an input and transforms it into a specific output based on a defined rule. This rule is consistent and applies to each input, ensuring that the same input will always produce the same output. This rule applies to each input, much like how a machine operates consistently on different items, producing the same result each time. We call this rule a function. It is a fundamental concept in mathematics that helps us understand and describe various processes. Think of a vending machine. This everyday example can help us grasp the idea of a function more clearly. You input money and select an item. The vending machine processes this input according to its internal rules. The machine processes this input and dispenses your chosen snack. The input, which is the money and the selection, leads to a specific output, the snack. This process exemplifies a function. The vending machine's operation is a clear example of how functions work in real life. Functions are powerful tools in math. They allow us to model and understand relationships between different quantities. We use them to model relationships between quantities. For example, we can use functions to describe how changing one quantity affects another. They help us make predictions and solve problems. By understanding functions, we can better analyze and interpret data, making informed decisions based on mathematical models. Every function has a domain. The domain represents all the possible inputs a function can accept. Think of it as the ingredients you can put into our mathematical machine. Let's revisit our vending machine example. The domain would be all the valid coin and bill combinations you can insert. It might also include the buttons you can press for your selection. In mathematical terms, we often represent the domain with the letter x. It's the independent variable in our function. Now let's talk about the codomain. The codomain encompasses all the possible outputs a function could produce. It's like a menu of potential results. Imagine the vending machine's display window. It shows a variety of snacks and drinks. This represents the codomain. However, the machine may not have every item in stock at all times. In mathematical notation, we often use the letter y to represent the codomain. It's the dependent variable, as its value depends on the input, x. While the codomain represents all possible outputs that a function could potentially produce, the range focuses on the actual outputs a function produces when given a specific domain. This means that the range is a more specific subset of the codomain. It's the subset of the codomain that the function hits. To put it simply, the range is the set of all possible values that the function actually outputs. Let's say our vending machine only has a few items in stock. These items represent the codomain, the total set of possible outputs. When you input your money and make your selection, the machine dispenses one of these available items. This represents the range. The range is the actual item you get, not just any item that could be in the machine. In essence, the range is the part of the codomain that is actually used by the function for a given domain. So while the codomain is the theoretical set of all possible outputs, the range is what you actually get when you use the function with specific inputs. This distinction is crucial for understanding how functions work in mathematics. Section 5. Codomain versus range, a clearer picture. The distinction between codomain and range can be subtle. Think of the codomain as a larger container and the range as the items actually placed inside. Consider a function that squares any number you input. The codomain could be all real numbers. However, the range would only include positive numbers. This is because squaring any number, whether positive or negative, always results in a positive number. Understanding this difference is crucial for accurately defining and analyzing functions. Section 6. Illustrative examples. In this section, we will delve into some practical examples to better understand the concepts we've been discussing. Let's solidify our understanding with a few examples. By working through these, we can see how abstract concepts come to life in real-world scenarios. Consider the function f(x) equals x plus 2. This is a simple linear function, but it can teach us a lot about domains and codomains. If our domain is all whole numbers, then our codomain would be all real numbers. This means that for every whole number input, the output can be any real number. However, our range would be all whole numbers greater than or equal to 2. This is because when we add 2 to any whole number, the result is always a whole number that is at least 2. Now imagine a function that outputs the types of planets in our solar system. This example helps us understand how functions can apply to more than just numbers. The codomain could be all celestial bodies. This includes not just planets, but also moons, asteroids and comets. But the range would be limited to the specific types of planets present. Rocky planets like Earth and Mars, gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. Each type of planet falls into a specific category within our solar system. These examples illustrate how the range can be a subset of the codomain, depending on the function and its domain. By understanding these relationships, we can better grasp how functions work in both mathematical and real-world contexts. Through these illustrative examples, we see that the concepts of domain, codomain, and range are not just theoretical ideas, but practical tools that help us describe and understand the world around us. Whether we're dealing with numbers or celestial bodies, these principles remain consistent and invaluable. As we continue to explore more complex functions, keep these foundational examples in mind. They will serve as a guide to navigate through more intricate mathematical landscapes. Thank you for joining this lesson on illustrative examples. Let's move forward with confidence and curiosity. Section 7. Common pitfalls and how to avoid them. One common mistake is confusing the codomain with the range. Remember, the codomain is about potential outputs, while the range focuses on the actual outputs for a given domain. Another pitfall is not defining the domain clearly. A well-defined function should specify its domain to avoid ambiguity. To avoid these errors, always start by identifying the domain and codomain, then carefully analyze the function to determine the actual outputs, which constitute the range. Section 8. Conclusion: Mastering the concepts. Mastering the concepts of domain, codomain, and range is essential for understanding functions. These concepts provide a framework for analyzing and interpreting mathematical relationships. Remember, the domain represents the input, the codomain encompasses the potential outputs, and the range focuses on the actual outputs for a given domain. By grasping these concepts and avoiding common mistakes, you can confidently navigate the world of functions and unlock their power in various mathematical applications.